Hello, Black Hat. Thank you for coming and waking up early today. We're going to talk about reverse engineering. And hopefully you're going to enjoy the tool, which is the important bit of the talk. So the tool is already on GitHub. It's free, as in free software, MIT license and BSD. All the components are MIT and BSD. You can do reverse engineering without doing any assembly and even without doing any C. So if you know how to do some Lua scripting, that should be enough to automate like a fair bit of reverse engineering. This talk is really about taking a new approach to reverse engineering. I have way too much content. That said, feel free to interrupt me, raise your hand if you have questions, and feel free to make some noise if you like it. So who am I? So this was my first research ever at DEF CON 16. That's like 8-9 years ago now. So it was about like finding, the way interruption 10 in the BIOS was handled by all the industry was wrong. And this led us to write a single exploit, which would work against all the BIOSes on the planet. BitLocker, as far as I know, it was the first exploit against BitLocker. TrueCrypt, and all the minor full disk encryption software. So that was kind of rad. The password was in plain text in memory forever in all those software. Another research I did for DEF CON and Black Hat some time back was backdooring a BIOS. So the state of the art back then was, if you're familiar with the FRAC article from the people from Core Security, basically, the state of the art was like, you take a BIOS, you identify the checksumming routine, you would inject a new function inside the BIOS, which would be malicious, and then compensate the BIOS and flash it back to your motherboard. This way, you could infect one motherboard. So instead of doing this, we took the best open source BIOS available, Core Boot and CBIOS, and we engineered from scratch the BIOS with malware inside. The benefit would be, instead of infecting one motherboard, we would infect 300 different motherboards. And that was kind of cool. So the MIT technology review was like, wow, that's a computer infection that can never be cured. Forbes liked it too, like they did a paper on it and stuff, which leads like imaging the kind of, online presence it gives me. You're mostly famous for writing malware. More recently, last year, we presented at Black Hat this attack on NetBIOS and SMB. If you're familiar with the traditional SMB relay attack from the 90s, really, we discovered that you can do the same thing from the internet and steal Active Directory credentials from the internet. That's work we did with my team at Salesforce. And so it was the first attack against Windows 10, the week it was released. And there's no fix against it. So if you still allow outbound SMB traffic on the Windows network, basically there's no fix. Questions so far? Disclaimer. So what I'm going to present today is my own research. My employer doesn't want to be associated with it in any way, which leads to this slide. Thanks to the Electronic Frontier Foundation for providing legal assistance. They've been pretty amazing on this. If you do reverse engineering, especially if like I do, you live in the US, it's a serious matter. And the folks from the EFF provide free assistance, and they actually have lawyers who are super competent on the topic, and I could not afford anyway. So kudos to them. Agenda. So today we're going to talk about the Witchcraft compiler collection. I'm going to introduce quickly what are the components. I'm going to show you how to transform a binary into a shared library. So we will call this libifying. Then I will show you how to take a final binary and unlink it back to relocatable object files that can later be relinked in either a new binary or a shared library. Then I'll show you how to transform a PE file into an ELF. And then we'll do some proper witchcraft. In particular, I'll show you what you have reflection-like capabilities, much like in Java, but without a VM for binaries. Of course, none of this is supposed to work. So if any of you are computer science teacher or something like this, you might get a stroke. If we have doctors in the room, please monitor for each other. Okay, let's do it. I have way too much content. So the tool set is comprised of mostly 3 binaries. There's a linker, there's a core compiler, and there's a dynamic interpreter. I call them compiler, but they really take binaries as an input and not source code. And based on those binaries, I've built a number of utilities on top of them, which are mere Lua scripts based on those tools. So the target, the host machine, has to be a Linux machine, but the binaries we analyze not necessarily. I'll show you in particular how to analyze dynamically ARM binaries on an Intel Linux machine without a VM. Let's start with the libification. So out of the 3 components, WLD is like the linker, the Witchcraft linker. So what's this libification thing? Well, we're going to try to take a binary and transform it back into a shared library. So let's just start with a demo. You guys get to see this? It's a bit small, isn't it? Better? Much better? How about that? Yeah? Okay. So, here is the source code of the demo. So basically, we're going to take proftpd. Somehow, I'm going to transform it into a shared library, proftpd.so. I'm going to show you how that works. And then this C code does what? Basically, it uses dlopen to load the shared library in memory. And it looks for a symbol inside this shared library called PR version get string, which returns inside proftpd the version of proftpd. And we're just going to do a printf of that. So how do we get proftpd to be transformed into a shared library? Basically, the magic happens here. So we take proftpd, we copy it into /tmp, and then we libify it. And automagically, that's going to transform proftpd into a shared library. So I'm going to do it with the makefile first, and then we'll do it like manually. So now, if I run the generated executable demo1, you can see that the version of proftpd.so is 1.3.3d. And that really comes from, it's really a function inside proftpd. So that's fucked up, right? That's not supposed to work. So how come it does? So we did exactly this. I can redo it manually if you like. But so basically, we copy proftpd into /tmp. We verify it's initially an executable. If you run the file command on it, it tells us, okay, it's an executable. And then the Witchcraft linker will patch it somehow into a shared library. And then we can invoke, we can invoke it and load it as a shared library, which is what dlopen was doing. What's amazing though, so I mean, if I look into /tmp, I should have the proftpd thing still there. Maybe. Okay, let's do it manually. Okay, so proftpd right now is an executable. WLD, libify, proftpd. No, that's not what I wanted to do. Menace libify works better. And now if I ask it, okay, what's the type of this thing? No, it's a shared library. Okay. What's amazing though, it's also still a valid executable. What just happened? Okay, this is so cool. Let's take a minute. Yeah, I'm pretty proud of myself. That was a good one. Okay, so what did we really do? We only really patched one byte. So if we compare the original ProFTPD with the one we just patched, we transformed in the header, the ELF header. We basically just changed the type from you're an executable to you're a shared library. And you would think that makes no sense. It actually does. Okay, so that's the source code I showed you. There's a couple reasons why this works. There again, if you're a teacher in computer science, you might be like, that makes no sense. But in reality, if you're a hacker, you might know the way ASLR has been introduced in the kernel. When was that? When did we introduce ASLR in the Linux kernel? Okay, what's ASLR? Okay, randomization. So the idea was like, we'd like to have executable every time you run them to execute at a different address for basic security reasons. The idea being, if you hardcode offsets, that's not going to work anymore. So instead of recreating a whole toolchain and a whole compiler and all that, the trick in kernel 2.6.16, so that's over 10 years ago, was to say, we're going to make shared libraries executable. Because shared library are supposed to be, I mean, they can be loaded at any address in memory, okay? Unlike non-randomized executables. So the trick in the kernel, you can look at the patch for this 2.6.16 and on, was to say, in kernel land, if the ELF header is of type etexec, which is the old executable way, or if it's an etdin, which is really a shared library, then it's a valid executable, and you can run it. So what I just did by taking this ProFTPD binary, which cannot be randomized because it was compiled this way, and patching 1 byte, is to create a non-relocatable shared library because it cannot be loaded at any address. It's only valid if it executes at this given address. But interestingly, yeah, it's still a valid binary, and now we can pass it to dlopen, which is a function inside the dynamic linker, responsible for, yeah, loading like your shared libraries and handling relocations. So the benefit is I don't get to do any of this manually myself. dlopen does all the work for me. All I did was really patch 1 byte. That's cool or what? Thank you. Okay, fasten your seatbelt. That was the most normal demo of my talk. Okay, let's play with Apache. I like that one a lot. Okay, I think I have 2 demos for Apache. Let's start with the... So basically, I'm going to call, inside this C function, I'm going to call ap-get-server-banner, which is a function inside Apache. Apache is already compiled as a shared library, if you like, because it supports ASLR. Okay. So if we ask what is the file type of Apache, it's actually a shared object already, okay, because it's being compiled with the ASLR. Now the real bizarre bit, get ready for this, we're going to compile this C code by linking against /user has been Apache, which is a binary, right? So you're not really supposed to do that. If I look in particular at the way this binary is now linked, you ready for this? Okay, so this is listing all, inside this new binary I just created, all the shared libraries linked against it. What do you think of the second one? What? And amazingly, it works. So this C function inside Apache, we just called it from inside your own C code, and in the same, in the same way, this Apache function returns like, a banner associated with like the current version of Apache. This is cool or what? Okay, I can show you right now another way to do it. So right now I did this statically, right? Like I write my own code and I'm linking against either this ProFTPD stuff we patched or Apache. So the Witchcraft compiler also comes with an interpreter, which allows us to do this dynamically without writing any C code. So the script, it's a fully scriptable language. I'll explain you more about this. But a way to do exactly the same thing in 3 lines of, I don't know exactly what kind of language that is. It's actually the language of the Witchcraft compiler, which is reflected C API plus Lua. So we can call directly this function. Okay, so this loads inside the dynamic Witchcraft interpreter /user bin Apache 2. It makes all the functions from Apache available to call inside the interpreter itself. And we can just like call it, put the result into a variable A and print A. And if we run that, hopefully, yeah, the result is the same. That was cool or what? Okay, so that's exactly what we just saw. So the idea already was to take a binary and transform it back in. To take a binary and transform it back into a shared library. How about we take a binary and we transform it back into relocatable object files, which is the typical output of a compiler before the linking process. The benefit of this is even if I don't have the source code, basically if I can come back to relocatable files, I can reuse any function in there and link it into my own projects. To put it in other words, the typical approach to reverse engineering is, so you have source code, it gets compiled to relocatable objects, and gets linked into binaries. And typically, the way people do reverse engineering is like, okay, I'm going to take those binaries and try to get back somehow to the source code. There's a number of reasons why this is not going to work super well. In particular, well, like the compiler adds its own routing to it. Like, we're working with an Intel architecture, so you have all the problem of like, what is the size of an instruction on a CISC machine, things like this. So instead of doing this, yeah, I'm just going to use the Witchcraft compiler collection, which takes binaries as an input and gives back relocatable objects. So I call it a compiler, but it doesn't at all work like a compiler, right? It doesn't take source code as an input. The reason we call it like this is the command line is very close to GCC. So to get the same output as GCC, you give it the binary as an input instead of source code. You give it pretty much the same arguments as you would with GCC, and magically you get the same output. So a thing to notice with WCC that the front end is built with libbfd. So it's actually, what is libbfd? You guys know what it stands for? Yeah, big fucking deal. So the idea was like, at some stage, the GNU project were like, okay, we'd like to have a uniform way to work across architectures and to work not only across like, physical architecture like ARM or MIPS or whatever, but also across file formats. So libbfd can work with like PE files, COF, exotic stuff. And the benefit of writing my compiler with this is that my input actually does not need to be an ELF. I can give it a PE file as an input, for instance, and get an ELF as an output if I like. What? So I'm going to show you a full demo of how this relinking thing works. Okay, so this is a very small application which just prints a string. But interestingly, it has a whole bunch of relocations. So not only, I mean, when you're importing functions like this, for instance, printf, so you have a jump to like the procedure linkage table, which has a pointer to the global offset table. And basically, when you execute the binary, the dynamic linker is responsible for finding printf in the libc. So knowing that printf is inside the libc is hard-coding inside your binary. But it has to find the path for the libc, load it in memory, and modify your GOT so that whenever you try to call this function, the pointer inside the GOT is going to be initialized, assuming you don't do lazy binding. Well, anyway, strings, for instance, like this string in yellow or this string in yellow, they're in different sections, right? The static strings end up in the read-only data section. So the text is referencing data which is in another section, and there is a relocation for that. And the dynamic linker upon execution is going to initialize that too. So long story short, this covers all the type of common relocations, right? To other sections, to functions and stuff like that. So let's compile this quickly. Okay. So this is the original binary. It does hello black cat. Okay, big deal. If we look at the make file, so we're going to take, so first off, okay, the first line we do compile small, which has just run and prints black hat. Then we use WCC to take small and produce a relocatable object file out of it. Okay? And then we relink this relocatable object file into small2. And the question is, does small2 run? And does it produce the same outputs? And possibly, does it have the same checksum? So the amazing thing is that small2 does run and does produce the same output. Okay? Thank you. Okay. And if we look at the checksums, they're not the same files. So to be fully honest with you, I don't handle yet all the type of relocation that are in theory supported by the Intel compiler. I mean the Intel specification. And for other architecture, there's also other type of relocations. So your help is most welcome if you want to contribute to this tool. Like, I think we have a good basis. It works in, typical cases. Now, you might find exotic binary or produce exotic binaries on purpose that are going to defeat the compiler. Feel free to submit them and to submit patches. That would be great. So that's pretty much what we just explained. Okay, I think the next slide is my best slide ever. You ready for this? I think it's self-explanatory. So we're going to take a P file and try to transform it into an ELF. Because why not? So I'm actually going to, let's do it manually. So I'm going to take Chrome. Yep. Actually, okay. So I copied Chrome into /tmp. Okay, it's a 32-bit P file. And we're going to use WCC to transform it back into an object file. So the command line is very similar to GCC, right? If I want object files, I use -C. So the input is going to be Chrome, and the output, for instance, /tmp chrome.so, because why not? Or chrome.o. Here we go. What did I do wrong? Okay, please give your hands to your neighbor. We all gonna worship the demo gods together. Fuck that. Okay. Okay, I'm out of sync with like you know, I keep patching the bug that people report on GitHub, so I'm not quite sure why this doesn't work, but it's supposed to work. So the idea is there again, since we're using libbfd as an input, I mean, as a parsing library, the input does not strictly have to be an ELF. No real question, what is the point in doing this? Because my kernel doesn't have the NT primitives anyway, right? So like if Chrome is asking like, okay, I need NT underscore whatever function from the Windows kernel, my POSIX system is not going to know what that is. So you can still call pure functions this way. So if the function, you know, if you have a function in Chrome that you know, you have identified as being useful and is self-contained, like it's not importing any function from the NT kernel or anything like this, that will work. To do something better, to be honest, I think we could really run this chrome.exe transformed into an ELF on a POSIX machine by leveraging the API of Wine, which is basically already ELF formatted and does provide somewhat an equivalent of an NT kernel. This is left as an exercise to the reader. If you want to submit the patch, I would absolutely take it. Okay. There again, I'm sorry for any computer science teacher like that. That's going to be tough. We're going to run an OpenBSD binary natively on Linux without a VM. Because why not? Okay, so here it goes. That's the binary we're going to run. So if I try to run it like this, Bash is telling me no such file or directory, which is bizarre because the file exists, right? So if I ask strace, like, okay, why are you not running this OpenBSD binary when I try to execute it? It tells me also no such file or directory. So even, you know, even execv didn't work. If you look at the kernel source code of what's happening when you try to do this, basically when you try to run the binary, it gets loaded because it's a valid ELF. It gets loaded in memory, and then the kernel looks for the dynamic linker. And the path of the dynamic linker on this binary is /user libexec ld.so. Let me copy this. So that's the typical path of for a BSD binary. Let me verify it's a BSD binary, by the way. OpenBSD, okay. So of course, this dynamic linker path, I don't have any such file or directory, okay. So the error message is really coming from the kernel. Okay. So how are we gonna run this on Linux? So I could patch the path of the dynamic linker to provide it the dynamic linker of Linux. Instead of doing this, I'm gonna copy my real dynamic linker to the path that the binary is expecting. That's a bit less intrusive. Then I have a problem of, I mean, the functions inside, basically the name of the libc inside the OpenBSD binary is called libc.so.62.0. Even if you're not a Linux expert, that's not the name of my my libc library on Linux. Mine is really called libc.so.6. So we're gonna patch this. I do this like a barbarian using sed, okay? So we're gonna patch this original binary, transforming like this name by libc.6. And we're gonna chmod it plus x, and then it will almost run. There will be one problem left. It's gonna ask me for a missing symbol at exit. Opa. That does not exist on Linux machines, but does exist on, is expected by the binary. So basically the way around this is we create a stub for it in C with the same function prototype. At exit does nothing, right? It's basically calling destructors. It's initializing destructors so that when the binary exits, you can call those destructors. For the purpose of this demo, we don't really care what's happening once you exit, okay? So we're gonna create this small shared library like this with the missing function prototype and LD preload it. And okay, so I can show you the original source code of the fmt.c as it was compiled on the BSD machine. It doesn't do anything interesting. It basically does a printf of static, toto, static. Great. And if we tap make, it just did the printf for me of static, toto, farbas blah, static. So we just run an OpenBSD binary natively on Linux. What's the limit of this? So this works because there's no system call done inside the binary itself, right? Like all the system calls which are done are basically done inside shared libraries. And by loading the appropriate shared libraries, I'm tricking the system into calling the right system call instead of calling OpenBSD system calls. Now, if the binary was, for instance, statically linked and was doing itself raw system calls from the binary, well, we would have to trick it and patch that inside the binary to compensate the system call. Make sense? Too easy? That's cool or what? Any questions so far? It's just too easy? Okay. Binary reflection. So that's beautiful. So binary reflection, what are we talking about? If you tell me a reflection without a VM, I don't even know what that's supposed to mean. Let's say I would like functions equivalent to reflection in Java. So being able to load applications, enumerate the function prototype, instantiate them in memory, and call them as I like. So we're going to do exactly that, but without a VM. So the magic happens around DL open, like we showed initially. So WSH is, okay, I showed you first how to unlink, so the dynamic linker. I showed you the WCC, the core compiler. Now I'm going to show you WSH, which is the Witchcraft shell. So it's really built around Lua, and the trick is whenever you load a shared library using DL open in memory, POSIX says the dynamic linker has to keep a cache of all the functions loaded in memory along with their address. So if I can dump that, basically I know all the functions which exist in memory and I know where to call them. In terms of prototyping, I can cheat even if I don't know exactly how many arguments the function expects. I mean, on a 64-bit machine, basically, imagine you have a function taking 3 arguments. What happens if I pass it 4 arguments? Well, I'm initializing an additional register, which is not going to be used. Nobody cares. If it was on a 32-bit machine, it would be like passing additional arguments on the stack, which will also never be popped and never be pushed back. So long story short, you don't exactly need to know the exact prototype of a function to call them. And notice that we didn't do any disassembly and we didn't do any decompilation either. Okay, I'm going to skip this for now. Too much text, not cool. Proper witchcraft. So assume for now, we get this reflection stuff to work, and I edit basically a very small Lua interpreter just so that I can get back the result of my functions and I can pass arguments easily. Okay. So the resulting programming language, which is basically reflected C plus Lua, I call that Punk C because it allows you to write almost C with some tricks. So that's the language of the interpreter itself. You can type the commands directly inside WSH, or you type all the commands, the exact commands you would type in the interpreter. You write them in a text file. You call that .wsh, and this is it. The Witchcraft shell will understand that those are commands and this is a script. Of course, you can use the traditional shebang mechanism if you don't want to call it .wsh. Demo time. So I'm going to show you, this is going to go really fast, but this is cool. So here is the script I'm going to execute. Opa. You can see that I'm basically typing commands in there, and they're going to be executed. Okay. This is going to be too fast, but this is going to show you a bit like what are all the capabilities of this tool. So we can load libraries. I can load Apache. If I ask him, show me the libraries in memory, there's more libraries. Okay, I can get a mapping of the programming header or the section headers. To verify it's consistent, I can actually brute force the address space using msync, which is a function which is supposed to synchronize back a page to disk if it's mapped. So this allows you to brute force anything, even if /proc is not available, but the heap, which is not backed by files, unless you're using a map, whatever. You can call things like getPid, you can get like a list of all the functions available in memory and their addresses. You can call those functions, you can ask information about memory location. You can grep, so you can grep stuff in memory. The result of grep being a function itself. You can turn that into JSON that you can dereference later on. I'll explain you more about that. You can search things in memory, like functions by name. You can call those functions like we just did before, displaying banners. We can use breakpoints, which are not backed by interruption 13, by interruption 3. I'll explain you that too. We can use C functions directly from the shell. We can xdump memory. What else can we do? We can get information about memory locations. Okay, so if I do a malloc, I can get the return pointer, ask him what it is. So all that is pretty trivial. When the application crashes on read or write and stuff like that, the application does not die, which is cool because it's not ptrace based. You can get context about all the functions you called. I'm going to do all that manually later on, like, don't worry. For the purpose of my demo, like, just assume this stuff works. So right now, we're doing this with an Intel binary. Because we loaded like Apache and SSH in memory. Okay. We can export headers in C if we want to compile them later on. We can call main. We can call MD5 functions outside and stuff like that. Okay, so that was cool, but that was on an Intel binary. Why am I showing you this? You ready for this? Okay, we're going to do the exact same thing. But right now, I cross-compiled WSH as an ARM binary, and I'm using a weird mode of QEMU, which does JIT binary translation for me in memory. So basically, right now, I'm running an ARM binary without a VM on my Linux machine, which is Intel-based. And as you can see, like basically the output of this command is the same as the previous one. So we can debug pretty much fully on binaries, without a VM. That's awesome or what? Thank you. Since that was really fast, I'm going to redo it manually with you more slowly. So let's start WSH. It typically expects a binary. I mean, you can pass it an optional binary as an argument. So let's load, for instance, SSH. So WSH is loading SSH in memory. I get a prompt back. Let's take a look at the commands available. Okay, so all those are like built-in commands. Okay, things like xdumping memory, information about memory mappings, information about symbols, stuff to search. So functions like grep, which allow you to grep any mapping, including the heap. You can load more than one library. So for instance, right now I can ask it, okay, show me the libraries that you have loaded into your address space. It's worth understanding this is not working like a typical debugger where you have a debugger debugging a debuggee. Since I'm using dlopen, what the interpreter is doing is loading, in this case, SSH and all its dependencies inside his own address space and not inside another address space. The benefit is you don't need ptrace. And another advantage is that when the Witchcraft interpreter is examining his own memory, he's at the same time examining, like, the memory of SSH or whatever program you loaded. So let's load one more program. So for instance, let's load let's load Apache in addition. Okay, so after loading SSH, I had 23 libraries. I also loaded Apache, so hopefully I have more now. Okay, now I have 28. And you can see that all the dependencies of both SSH and Apache have been mapped in memory. So what are the functions available for me to program with that? Well, the command is functions, not too hard. So I have the library where the function lives, the name of the function, and then a bunch of information. In this case, I have like about 8,000 functions that are loaded in memory, and then I can call directly from my interpreter. Okay, let's search for stuff which returns versions, for instance. Okay, 17. So let's call APR version string, for instance. We would assume returns a string which is like the function of libapr, which comes with Apache, right? So if I want to do this, I can write something like this. And that's why I used Lua. It's to be able to have, those variables living in memory and existing and stuff like that. So if I want to call it with 0 arguments, I just call it like this. And hopefully, print of A is going to return me the version of libapr. This is sick or what? Okay. How about another one? GNU get libc version. So if I wanted to pass it arguments, I'll just write it something like this. Okay, and I just call this function inside the libc with argument for 1, for 1, for 1, for 1, 4. And that's the version of my libc. This is awesome or what? So the beauty of using Lua is that you can return more than one return value. So actually, every time I call a function like this inside the interpreter, it transparently also returns me into a second variable, a context, which describes what happened when you try to execute this function. So if I dump it, it tells me when you try to do this call here. So this function came from this library. He called it with one argument. Okay, one argument. Error number is 0, which means success, no error. And the return value was this, and no signal was associated with this. You might be, what's the point in doing this? The point is to have automated function prototyping. So let's take, for instance, we said libapr. There's a building fuzzer inside the interpreter. So okay, if I type this, it's going to look for any library which has APR into his name, enumerate all the functions in them, and call them with random arguments. Hopefully that's going to somewhat crash. Okay, so that's what it's doing right now. So the colors mean like, okay, if you segmentation fault on a read, like typically here, it's green, it tried to read 0, which is not mapped, so that crashed. When it's red, it tried to execute the associated pointer. So why is this cool? Well, if I reload it, okay, Apache. If I ask it in memory, show me the prototype of all the functions you've learned through this execution, it's going to tell me, okay, I tried to execute, for instance, IO's printf, and I discovered that the second argument is an input argument. So this is annotation on top of the prototype of the function. If you ever read the source code of Microsoft, because it leaked or because you did some consulting for them or whatever, they were trying at some stage to annotate every function like this, like what is read, what is written, and what is executed. The benefit for it being to do enhanced static analysis. So basically, the tool can discover this by itself by trying to execute, with chosen arguments, all those functions. And it tells you, for instance, like, okay, this function here, the first argument is a function pointer. We didn't disassemble, we didn't decompile. This is awesome or what? To be fair, I never thought that would work, but it does. So we can do stuff like grep. Let's grep for lib, for instance, in all the address space. So all the function, all the shared libraries and all the mappings. Okay, so that's grep. And the return in A is actually a table which I can dump, and it will contain all the offsets of A, that matched. So it found like 170 occurrences of lib in memory. This is way easier than trying to use a debugger or disassemble. So what other functions do we have? Yeah, I guess that'll be it for now. Okay. A cool thing is you can export a basic prototype for all those functions that will generate you C headers, so you can relink against shared libraries. And to be honest, you don't. What the fun? You don't actually need for your compiler to be happy and to understand what you mean. You don't need to pass them a whole lot of information. If you just define the function pointer as a void star, which is going to be like 8 bytes on a 64-bit machine, and you don't even tell them how many arguments the function take, GCC is going to be happy with that, which is cool. Okay, that was the Witchcraft demo. We did the ARM one. Future work. So if you want to contribute patches, stuff I would really like right now, my heap memory allocator is using the same memory allocator from the libc, so ptmalloc. Then the binaries we analyze. This sucks because if we have a memory corruption, I'm going to corrupt also my heap. So using a secondary heap allocator would allow us to segregate that. And when there is a memory corruption that we trigger in the debugged application, we wouldn't trigger memory corruption inside our own application. So that would be cool. We could do that using ptmalloc itself by defining another arena for the heap. But I think a secondary memory allocator, by looking against another version of ptmalloc or Douglas malloc, would do. Remote debugging, I've actually already merged this. So if you look at the example on GitHub, there's already an example of doing remote debugging. Process injection, so something like if you have a running process, could we inject WSH inside a running process? The limitation I have right now is, I explained to you that when we take a binary and transform it into a shared library by patching 1 byte in the header, the resulting binary is not relocatable. Okay, it's not a real shared library in the sense it has to be mapped at a given address. So to avoid conflicts, I compile WSH with a custom linker script at a given address, which is different from the one typical compilers would give you. This means that it's not a shared library and I cannot inject it. So yeah, a bit of work to do on this. Shadow mapping, internal tracing, stuff like that. Something I really like is to use the output of ltrace or strace on a binary and transform that directly into a WSH script. That's not too much work. I think that should work for next time. Any questions? Yep. I can't hear shit. Can we pass in the microphone?
Yeah. Is there a risk that some kernel developer will see some of this as bugs and try and fix it so it won't work in future?
I mean, the only thing we're leveraging from the kernel is the fact that basically ASLR works. I don't think the trade-off would be, in favor of breaking my tool, to break my tool, to destroy 15 years of security on the Linux kernel. So that's rather unlikely. But honestly, like all the stuff I'm using are like, POSIX features. They're not bugs, so that's not gonna get fixed. That's how it's supposed to work. I mean, I understand it's counterintuitive, but it's very much standard. In particular, the trick of using dlopen and of dumping the cache of the dynamic linker is not libc specific. It's a POSIX compliant requirement, which means you don't have to use the libc. If you use micro libc or other libcs, that's also going to work. So it's fairly portable, actually. Good question, though.
Wouldn't work on Linux. Oh, Linux, Windows.
Windows, I mean, it's a good question because they're starting to be POSIX compliant to a degree with Ubuntu. I haven't tried much, to be honest.
But the Ubuntu stuff runs ELF binaries.
Yeah.
So if you go to D, then you don't have all those exports.
Yeah.
And stuff like that.
It's a fair question. It's worth trying to compile WCC on a Windows machine and let me know. I haven't tried, to be honest. I don't do a whole lot of Windows. Any other question? Well, thank you for your time today.